We have Professor Dr. F.P. Krishna for this session as a resource person. He has long experience in the field of remote sensing. He did his PhD from he did MTech from IIT Roorkee, and then served in one of CSIR lab, and then joined BIT Mesra. He is still in the BIT Mesra as
one correction, not CSIR, but Ministry of Environment and Forest Institute.
Thank you. Thank you. Thank you. So, participants, we start this session. Now, sir, now session is with you.
Thank you, Dr. Rathod, for inviting to deliver a lecture on this FDP, Faculty Development Program. And I hope I am audible. Is it okay? Voice is
yes,
okay?
sir. Yes, sir.
Yes, sir.
Yeah. So I welcome all the participants and everybody who's attached to this program. Wonderful other kind of material I would like to take added to lecture which we delivered earlier. So now I have got this opportunity, and then probably I'll try to do this, probably justice to the topic, as it is a very broad topic. So I'll say not in that sense that I'll cover everything, but I'll try. I hope my this presentation thing is visible on the screen.
Yes, sir. Slides are visible.
Okay, so I can start. So there's a topic that remote sensing in climate change studies. Actually, I can look at it in two ways when I'm talking to you. Is as our one of the PG course subjects as well that we are teaching here, and then where actually we start from maybe talking about fundamentals and then at length in terms of all the global concerns. But I think in a course like this, we must actually try to somehow remind ourselves about the kind of climate change kind of implications which are there, and then only remote sensing comes. So remote sensing, of course, we will try to do justice in terms of the tool which actually we have at our disposal in this technology that we are using, and various types of, in fact, not only tools, but you can say data availability, and then in fact the kind of potential that it provides to us. So that is what is we are looking for. And then of course climate change is something which we in general everybody is concerned, and then I think concerns are at various levels, various kind of applications areas. For example, if I can connect myself to that, then I can say, okay, I have been involved in maybe some Himalayan glacier and snow change cover studies where I have produced 2 PhDs also, and a number of papers. So that is another story, academic story. But similarly, in fact, some other speakers, as Dr. Jagannathan talked about phenology and climate change related phenology and forestry applications. This morning we heard Dr. Ramarao about agriculture, and then prior to that, ocean dynamics was being talked upon. So that all climate change perspective, somewhere they are connected, and they are already taught. So let me just start with a kind of remote sensing, that basics that we actually look for. But maybe we actually try to look at the data which is being acquired and information about any phenomenon and territory that is without a direct contact. So that is in general that we tell the students, and we remind ourselves that is what is this technology about. And then of course now using all the kind of techniques and data at our disposal, we have to produce some kind of a knowledge or even decision support system for targeted users. So that is what is where actually the kind of our this objective which will be made out in any studies. Accordingly, it has to produce knowledge, and then involvement of final users as stakeholders along the entire process of knowledge and products design and creation, which is essential to produce outputs which are really used and useful. So when we proceed like this, then the kind of this justification of this technology that we are using and techniques and data. So we can say we prepare ourselves with this kind of a workflow for any kind of a problem, real life problem or any kind of practical problem when we want to deploy this kind of a tool. So these are symbolics and some of the data samples and those things that we keep on discussing and finding out how much is available. There was a time when remote sensing data was not so freely available. Now it is available when we say Earth observation era. I'll talk about that later on. So doing that what actually has happened. And then particularly talking about past 5 decades, that has witnessed satellite remote sensing to have become one of the most efficient tools for surveying the Earth at local, regional, and global spatial scales. So this is spatial scale. So that is what is most important. So at whatever scales. In fact, earlier when remote sensing was started, maybe towards 80s or somewhere, so we were just talking about maybe one scale. Could we do it at multi-scale? So that is what was being attempted with using other maps. But now we have multi-scale, so local, regional, and global spatial scales. So now it is becoming that important for these kind of studies. And then such space-based observations, they have a non-destructive character. So in fact, that is why, in fact, we look at this technology with great hope that it can allow for rapid monitoring of the ambient atmosphere, its underlying surface below that, and the ozone mix layer. So many things which may be of concern. And satellite instruments, they can observe toxic or even hazardous environments without putting people or equipment at risk. So in fact, these are all kind of research areas where in fact the things are still developing and moving. And large-scale continuous satellite observations complement detailed field observations, and they provide measurements of unsurpassed volume and content for theoretical modeling and data assimilation. So in fact, here basically this kind of statement I am quoting from one of the very kind of nice journal, Frontiers of Remote Sensing, so Ludovic et al. So they have written a very good article in February 2021 publication itself. So some things they were actually very nicely summed up about maybe what kind of capabilities and where we are moving. And talking about this Earth observing system era. So in fact, we are all aware that with the launch of this Terra satellite of NASA, US that we say, US era began with this launch of Terra satellite in 1999. And a lot many sensor about this, and it's continuous. And Aqua also seeing more and similar type of sensors with better capabilities. And actually this has brought in the global coverage, frequent repeat coverage, high level of processing, that is easy and mostly free access to data that it is able to provide. So that is actually, we look at these Terra and Aqua satellites together. They carry sensors such as MODIS. MODIS, I think we are all very familiar with dealing in this area, geospatial domain and then remote sensing domain. So MODIS, many products, MODIS, and then measurement of pollution in the troposphere, that is MOPIT. They have daily revisit and various process data. So we'll slightly see these things also about MOPIT's implication and other things. So wherever such kind of factors that we discuss about those global climate change kind of researches which may require this. Then applications of sensor data, they have become widespread and applications have multiplied. So that actually with this capabilities becoming freely available in the public domain. So in fact, that has led many institutions and individuals who never used remote sensing, they also have begun to take interest in remote sensing. So that is why we also see that even we actually teach our students, and we see that our students have to get the data. So they use the word download. When we were studying, we were using the term like satellite data procurement, long and tedious process, involving a lot of cost. So in fact, that is just I'm trying to say that this basically gives a hint that that freely available data and these kind of data which are there. So this basically is Earth observing system era. Beyond that, now the situations have totally changed, and then these are all good data available, and then that is why our students say we have to download. So downloading the data, even we also download. Then also the availability of the processed data in terms of products such as leaf area index and land use land cover, they have become routine. So these some kind of processed products in which the data which are acquired basically using suitable algorithms, these are converted into some kind of application products. So these are going on, and then currently that is why the MODIS itself has 40 plus products. So we can see the list of products in MODIS, various types of products. And then active spaceborne remote sensing sensors, they use radar technology. That also has become prominent around this time and during the Landsat era. And the launch of European ERS, Japanese Earth Satellite, JERS, RadarSat, and advanced land observation satellites, ALOS. Then SRTM also, that we actually use largely to gather data for digital elevation. So these all kind of things. So actually maybe attributed to Earth observing system. So and era rather, sorry. And use of remote sensing, when we say some of the common ones that we talk, I will not say limited to this list that I'm just flashing before you. So these techniques, remote sensing techniques, the data acquired from various sources. So we basically look at numerous fields such as commonly geology, hydrology, meteorology, hydrology, oceanography, glaciology, defense, geography, commercial, economic planning, and humanitarian applications where disaster management, many things may come in. So, and you can add on to this list. So, not a very exhaustive list, but still we have these kind of domains which are being touched upon. That is just as a kind of basic kind of begging point for us. But looking at the significant interdisciplinary areas where remote sensing is playing a very good role, and in fact, that is not only away from anything which is happening on this planet. So, in fact, a lot of things that we monitor and study using the capability of remote sensing, that again, that we talk about either spatial implications or you talk about the temporal implications, that we actually look at many things that you can see here. Maybe let us look at natural resource management. So, natural resource management itself, in fact, allows us to in fact have the quantified details, and then maybe the land cover detail, and then what other kind of supplementary kind of things can be attached to that, and then we can go for some things where it is converted into some meaningful kind of representation of the quantity and quality, for example, agricultural produces, and then forestry in terms of those kind of implications where forestry people will be interested. And then management is in fact monitoring and in fact picking up the data and details, and that is again I'm repeating spatially and temporally, so that we are doing already. So many of us who are attending here, they are already familiar, but as a quick kind of reminder of these facts, so natural resource management would be there. Management of agricultural practices, for example, so it is more specialized, for example, related to land use, land conservation, and soil carbon stocks. So these are all, in fact, these days getting emphasis. And tactical forest firefighting operations in real-time decision support systems. So these are again some of the areas in which, then monitoring of land cover and changes over different temporal and spatial scales, even after a disaster event. So this is another area. Better informed forest and water management, evaluation of carbon stocks and related dynamics, simulation of climate system dynamics. So in fact, this is one of the very kind of pertinent thing, carbon also. And then improvement of climate projections and meteorological reanalysis products, widely used for climate change research studies. So in fact, whatever basic data is there, and then after that, some kind of products are there, and then that can be in fact factored to the climate change research studies, where models could be getting the advantage of using them into various models for predictions, and improving warning and preparedness being therefore also useful in disaster risk reduction. So in fact, a lot many interests, and again I'm repeating, not limited to this, but some of the very significant ones, and in which we can see there is a dimension of climate change is also coming in between. So and ultimately any change and anything that we can find as anomalous change out of all these studies can only be like at the moment not to straight away attribute to climate change, but there could be some kind of feed to study, some feed to research, and find out if there is some anomaly which is occurring due to any kind of this so-called climate change. So-called is not the right word. Let us say global warming, climate change, anything which is happening around us, if that is responsible for that. So some of the things where in fact remote sensing can play a very important role. Rather, it is playing, and then we are all in fact almost practicing people. So we are all involved in this, so including all of you maybe, so in some way or the others. So when we start talking about weather and climate, so in fact we actually start looking at the sun. So weather starts with the sun. So we start with any day, and we actually talk about how is the weather. So whether it is sunny. So sunny is one important point there, and sunny, and then sun actually takes care. In fact, if anything is happening, so in fact weather actually is there to be thought of. So weather and climate. Now actually we need to, I think many times we, or you might have also explained to your students, and maybe we ponder about all this. So basically it is the kind of time frame that actually matters when we actually try to distinguish weather and climate. So weather basically is a temporary behavior of atmosphere. So it is going on at any certain time and covering a small geographical area, and it can change rapidly. So this is how we understand and study weather is meteorology, and someone will study. So I think these are some basic things. Not only I'm trying to remind here to everybody, but you might already be telling your students also. And then climate, long-term behavior of atmosphere. So that is what actually we are talking about, 100 plus years, and then large geographic area, very slow to change. So any kind of characteristics of climate that we try to understand, or we try to tell the students, or we try to educate anybody, would be kind of lot of statistical analysis to be carried out, and which may be possible in terms of climate, when we are talking climatic variables and climate and then climate, that time frame. So that is how the huge quantity of data for that. So long-term behavior of atmosphere 100+ years. So now specific climates that we talk. So now area-wise geographical kind of positions on the planet Earth. We have polar climate that we already are aware that it is 90 to 60 degree latitude, and then basically what it has is cool summers and cold year round, and then dry. It is dry, so that is what is polar climate we refer. And then we talk about temperate climate, where you have the kind of this disposition of geographical location that between 60 degree and 30 degree latitude, and there are two seasons here. So we have winter, summer, and monsoon, everything. So all seasons we have, and variety of climate patterns they actually are observed in the temperate climate, and moderate precipitation, so rain and snow, including both of them. So that is how we actually talk about some of the kind of geographical considerations of these climates over the planet, and looking at maybe tropical climate where we have 30 degree equator and no to equator and no winter 1 year round. So that is, in fact, it has the kind of high temperature, rainfall, and humidity. So this is the kind of another tropical climate in terms of geographical kind of this extreme that we can see, and factors which affect the weather and climate. So in fact, why I'm talking about all this, it's not that I want to teach a basic here in this class, but it is something like when we start and then we actually try to connect to any kind of application area and tools and techniques. So my idea of talking about all this is to connect slightly to those basics where actually we are concerned, and then actually that advanced level of changes that we look at, and then advanced level of parameters and climatic variables that we look for. So basically where it starts. So after sun is one factor, then water cycle, then atmosphere and ocean. I think these are the major players, big players. So what we see is this kind of a that we say that hydrological cycle and these things which happen. So this is something we are all familiar. So this hydrological cycle, the only symbolic thing that I have kept here. So it is, you can see the starting with the sunlight and water cycle, you have the atmosphere and ocean. So how in fact the things move, and then whether it is continuing in a way, normal way, or there's a kind of anomalous behavior or anything. So there itself, the every key to every changes lie. So, and then how does the sun affect weather? So basically, when we talk about sun, it warms the atmosphere and ocean, then it creates climate zones. In fact, that is why in the very first slide that I said is weather and climate begins with sun. So it is basically sun which warms the atmosphere and oceans and creates the climate zones also that we saw. And then it keeps the water cycle going. So without sun, there is no water cycle. So this is what actually, and then it affects the weather pattern. So these are some of the things that we actually look at. So this is again almost like symbolic of the similar hydrological cycle, but here basically radiative exchange and transfer that you see, that the sunlight falling in, then what kind of component which is going out, where the what short wave component entrapped and long wave radiation which goes out, those kind of things. So we have to keep that thing in mind when we actually start looking at global change, and then any kind of things that can be captured through satellite remote sensing, and then some of the things where actually one has to look at those also, where it can play a role in understanding the behavior that we see or any kind of change here in these kind of parameters, natural parameters, which are supposed to in fact go on in a very kind of regular manner, where it is becoming, I'm again repeating, so what actually in the climate change thing, what we are actually trying to observe, any detailed study of any of the aspects that we can follow in this lecture also, or maybe even your individual studies, we are actually looking at those anomalies, any kind of anomaly, and that anomaly, once it is found, then we actually ring the alarm bell for any kind of climate change. So that is what actually one has to see what we can arrive at. So if it is a routine kind of thing and we want to just measure, that can be one thing. You can derive some kind of those kind of departures and changes, which is actually not desirable. So then we can see, yes, the kind of these impacts are there, and that will change in weather pattern and any kind of changes which are going. So some normal thing and then something abnormal. So that actually where we have to relate to, and then look at the tools available with us and techniques available with us that we can use. How does the atmosphere affect weather? When we actually look at atmosphere, basically is a mixture of gases that surrounds the Earth. So I think that is where the starting point, we have the gases surrounding us, the atmosphere. And then actually we have the 5 different layers, and every layer has different properties. Then air temperature and pressure change with altitude. And then that weather occurs in the layer closest to the Earth, so troposphere. So in fact, that is what we are mostly concerned, the troposphere, which is closest to us. So this is how, in fact, the quick kind of revisiting these kind of important implications. So in fact, we're researching more and finding out more about kind of different details. So here you can see those 5 layers. So you can see, so starting from closest is troposphere, stratosphere. So starting from your closest, I think this spread out is known to all of us. So in fact, nothing, there's no point in repeating this, but one can just see these dispositions that we are talking about. So from where we start, what is enveloping us, from there itself our concern starts, and then what warming we are talking about. So something, the impacts which are finally because of the climate change that takes place. And when again looking at the observation of climate systems, naturally we will be concerned about the spatio-temporal states and processes of the climate system. So now spatio-temporal states and processes of the climate system. So in fact, this spatio-temporal part is our part where we actually can play a role when we have the techniques and tools of remote sensing that we use, and to what extent we can deploy that and whatever is possible. So that is what we actually look at, the availability of the kind of techniques and data. And processes, of course, naturally one needs to understand. Say, for example, I want to work in an area, maybe Himalayan area and the snow and glacier, then naturally the catchment, right, I'm not familiar with the kind of hydrological behavior of that basin, then I'll not be going very far with only measuring map measurements of changes until unless I factor it into the kind of basin hydrology behavior and those kind of things. So I think just one example. Similarly, anything which is concerned with agriculture or forestry, similarly in any area, any kind of modeling may be there for the kind of maybe for agricultural products, and various kind of factors may be there. So any kind of climatic variables which are there, which is changing. So those processes, then some kind of model has to be there. So in fact, I'll not talk about those kind of models which are in fact known as global and regional model and those kind of circulation models. So in fact, that will be going too far. But I'll come down back to where we can connect remote sensing to these kind of things. So it is just one kind of visual that I'm keeping for you. Similarly, in the sense that it is again the kind of you can say universal process that we are all a part of this. And then if this is the imbalance actually is there, and then that is what actually we need to look upon in terms of our observation spatio-temporally, the states which are there. And then, and talking about global climate change, it is actually looking at identifiable change in the climate of Earth as a whole, which can last for an extended period of time. So it actually is something not local and maybe a kind of short duration thing. So what we are looking for is decades or longer. So maybe in that time scale we are talking. And when due to natural processes, it is usually referred to as global climate variability. So this is actually looking at natural processes, then climate variability term is usually used, and then usually refers to changes which can be caused by human activities that change the atmosphere. So in fact, that combination, and then we arrive at this. So in fact, looking at this climate variability and then human activities which can change the atmosphere. So this both put together, and what causes Earth's climates to change when we look at changes in the atmosphere. So in fact, first of all, the starting point could be there, some changes. And in fact, at this point of time, we can relate to many things that we have been hearing for a long time in our life, that ozone hole and those kind of things. A long time back when the kind of these concerns started, and then in the atmosphere. So those are things. So any changes in the atmosphere, otherwise by other biogeochemistry also of the atmosphere which is changing, and many kind of things which can happen. So any of the phenomena where we can play a role. So that is one. The natural processes, of course, here actually is a combination shown here. I can say that maybe not again limited to this, but you can see some natural processes. When you can look at maybe volcanoes, maybe tectonic plate movement is one of the kind of very accepted geological phenomena which is still at play. And changes in the sun kind of behaviors or maybe something happening. We hear that from time to time. And shifts in Earth's orbit. This is also coming in as one of the factors as natural processes. And then, of course, human activities when we look at, so that any activity which releases the GHGs, greenhouse gases. So this basically, when we come here, it is that way, looking at that kind of impact factor, which is actually human. So here, let us slightly go to some more facts. I think somebody's mic is on. Sorry. Please mute your mic. Somebody's mic is on so that others can hear clearly. Please mute your mic. Somebody, anyway, if you're able to hear me, there's no climate change. Evidence for climate change, when we look at maybe some of the reporting that we come across, maybe one of the samples that I put here about 11 of the 12 years from 1995 and 2026 as a case study. 1995 and 2026 were among the 12 warmest years since the mid 1800s. Between this span of time, 1995 to 2026, according to these 12 years, 11 of that 12 years were warmest years since the 1800s. And in fact, meteorological spring in northern hemisphere, so in fact, that has started coming more than 6 days ago. So some of the observed phenomena. So some of the evidences, and of course, warming is not due to natural causes. Here, it is again attributed to human-produced greenhouse gases are most causes. So sudden increase. So what naturally we are talking about, that might be contributing gradually, but human-produced greenhouse gases is actually multiplying. So that is actually of more concern. And some kind of data that you see from 1960 to 2005. So about maybe 0.5 or so. So that is the kind of data. Annual drop global temperature rise. So very significant 0.5 degrees only, maybe, but still this sometimes more, but on an average of frequency. So this, and in fact now IPCC 2021 is also out now, which is predicting about the rise of 1.5 degrees temperature, so that by the end of this century. So in fact that is going to be kind of disastrous. So we'll see more of that and out of our interest. No, somebody is saying something. Okay. No, coming to now greenhouse effect. So I think this is just maybe I'm putting here to kind of just address our concern. We'll go back to that part where we actually try to connect more. But here, sunlight passing through the atmosphere to Earth, so that is one part, and then something happens. So after reaching the Earth's surface, when it is reflected back through the atmosphere to space, and that actually, you have the after being reflected, you have the greenhouse gases, that is methane, carbon dioxide, water vapor, nitrous oxide. They actually trap heat in the atmosphere. So in fact, that is where in fact things started happening. Long waves go out, but short waves they get trapped, and then more of this means more of entrapment. And basically, this is a greenhouse effect that we know as a greenhouse, like in agriculture it is used, so greenhouses. And greenhouse gases act like a big blanket around the Earth, trapping heat. And greenhouse gases trap heat from the sun in the atmosphere after it is reflected. So in fact, the same thing. So this basically is the kind of without them. Otherwise, the positive part is there. If there is no greenhouse effect altogether, the greenhouse gases are not there, then Earth would be very cold, about minus 18 degrees C, and may lead to all water on Earth to freeze, the oceans to turn into ice, and life without would not exist. So in fact, when we say and talk about these concerns in climate change, greenhouse gases are the culprit. But at the same time, in a kind of balanced manner, if they are there in a natural process as it is, and they are there, then that actually helps the Earth. So that is what is not that we have to get rid of that in the natural process also. But it is in fact that this maintaining the temperature that we have, in which we have the existence of this oceans and other kind of water bodies and other kind of life which can survive. So that is very essential. But excessive green gas, that is what is the concern, where actually we look at this greenhouse effect. So greenhouse effect of that extreme, where it is going to in fact lead to a situation where it can be harmful, and that climate change thing which actually starts. And then GHG emissions, another one example I am giving from IPCC earlier report, 1970 to 2010. So you can see, in fact, the components that you have the fluorinated gases here, small layer on the top, but you can see CO2, fossil fuel, and industrial processes. So from there, whatever these kind of emissions which are in the atmosphere which are going. So it is in fact 1970s. It is close to this kind of volume that you see here. In fact, this equivalent is gigaton carbon dioxide per equivalent per year. It is shown in that scale. So this is what you can see, and then the increase 1972 to 2010, then carbon dioxide, forest and other land uses. So you can see another one. Then you have the carbon, this methane, the nitrous oxide, and then fluorinated gases. So in fact, those kind of estimates which are there, so it is all pulled through a lot of research. So that is in fact, we are all knowing that climate change research, we can get these reports very easily, and these details are now available. So that is what is the best thing. Now researchers only have to focus more on the kind of tools and techniques that we have. So in fact, now, so since 80s, there is a figure that almost the global temperature has increased by 1 degree C, and they depend on how much greenhouse gases. So in fact, that is why, in fact, after the industrial revolution, more of this, and then naturally, that is why we actually refer to this. And then there is another prediction of IPCC. So this assessment report of 5 of 2013, which was released in 14, that already predicts that the temperature could rise by 5 degrees C by 2100, unless countries around the world agree to minimize GHG. So in fact, there are various countries who have pledged already to minimize this, but one has to see the final result if they are able to do. And so much GHG is added that even if all emissions are stopped today, still the planet would continue to warm for decades to come. I think these are the food for thoughts for more research. So that is why it's not that I exactly want to describe this, but some of the key points that we actually talk and discuss, then that actually give us that kind of an imperative that we actually look at the tools and techniques available and do more and more research which can be beneficial either at our level, local level, or we networking too. So now global warming, actually when we talk, it is intensifying the water cycle, and then higher temperatures basically may increase the evaporation of water from sea, lakes and rivers, and warmer air holds more water vapor, resulting into more intense rainstorms which can lead to flooding, and then more floods where water runs off into rivers and streams, but does little to dampen the soil. And then another extreme is arrived at there is as increased temperatures can lead to drought. More of runoff, but more of this increased temperature as well, and then drought conditions. And then weather patterns across the world are affected over the period. And then basically this where actually we worry about this, the result as a climate change. And I certainly am tempted to take you to these some of the important conclusions of IPCC 2021, because this just recently released kind of this report under finalization. So this some significant facts as per the recent report of this Intergovernmental Panel on Climate Change. So they have said that it is unequivocal that human influence has warmed the atmosphere, ocean and land. So it is almost conclusively out of all the research studies they have arrived at till now. Then widespread and rapid changes in the atmosphere, ocean, cryosphere and biosphere have occurred. So here actually our research areas could lie: atmosphere, ocean, cryosphere and biosphere. So changes have taken place widespread. And then observed increases in well-mixed greenhouse gas concentrations since around 1750 are unequivocally caused by human activities. So in fact, the database that they have analyzed, that they have come out, so they have conclusively saying that this is not the natural rise, it is certainly aided by human activities. And since they have considered a period after 2010, so since 2011, what studies they have in fact collated and found that concentrations have continued to increase in the atmosphere, reaching annual averages of 410 ppm for carbon dioxide. So it is somewhere in the last decade it was lower than 400. Before that decade, earlier than that, it was lower than 300 ppm. So now it is 410. Then 1866 part per billion from methane and 332 part per billion from nitrous oxide in 2019. So this is some kind of data framework that they have actually come out with, saying some of the conclusive kind of findings. And land and ocean have taken up a near constant proportion globally, about 56% per year, of CO2 emissions from human activities over the past 6 decades without regional differences. In fact, that one can see that ability of the oceans as carbon sink, that is in fact what carbon dioxide is going out as emissions. It is surpassing all those things. So, and then human influence is very likely the main driver. Again, I'm repeating and reading their kind of findings. So that is just as a recent information that we should actually, that may look more interest in us for towards this research. Human influence is very likely the main driver of the global retreat of glaciers. We talk glaciers as indicators of climate change. So a lot of this retreat of glaciers in the 1990s, and the decrease in Arctic sea ice area between 1979, 1988 and 2010-19, about 40% in September and about 10% in March. So in fact, this is what the data they have analyzed, and they actually give these kind of projections. And there has been no significant trend in Antarctic sea ice area from 79 to 2020 due to regionally opposite trends and large internal variability. And then human influence very likely contributed to the decrease in northern hemisphere spring snow cover since 1950. So in fact, snow and glacier, in fact, that is taken as one of the very kind of strong indicators when one can see that something is happening, and spatially and temporally that can be observed. So we'll come slightly to that later on. It is virtually certain that the global upper ocean 0 to 700 meter has warmed since the 1970s. So it is stopped about 1 kilometer, less than 1 kilometer area, and then extremely likely that human influence is the main driver. So here actually you have other kind of implications like SST and those El Nino, La Nina, those kind of things, and then a lot of hurricanes and cyclones. So this is where actually SST thing, this warming can relate to. It is virtually certain that human-caused carbon dioxide emissions are the main driver of current global acidification of the surface of the ocean. Then global mean sea level increased by 0.2 meter in 1901 and 2018. So this is basically a range they are giving 0.15 to 0.25 meter. So on an average 0.2 meter. So mean sea level already has risen within this period. And average rate of sea level rise was 1.3 millimeter per year between 1901 to 1971, which actually increased to 1.9 millimeter per year during 71 and 2006, and further increased to 3.7 millimeter per year between 2006 and 18. So that means what? That rapidness you can see in the recent times. So that is actually multiplied many times, almost doubling here. So it is from 2000. This is actually between 2006 and 18 only. So that is very alarming. So that is what one needs to see. Then that lot of contribution through this melting of ice and snow. And I think that now effects of global climate change, when we talk, ocean as carbon dioxide sink that we see. So excess carbon dioxide basically is starting to harm ocean life. So that maybe ocean life may be one of the concerns. So all kind of ecology and then the kind of existence of aquatic life and ocean. So that maybe one can see. So that scale is shown here, how it is rising, and then you have the reef coral reefs, which are very important. The ocean as a kind of this ocean good health indicator. So in fact, that percentage change in calcification, that actually where it is low, mid, or high. So those kind of things. So you can see it is how it is reducing, and then effects of global climate change, melting ice and rising sea level. So here sea level rise caused in two ways basically: thermal expansion, the water expands and it warms, and melting of land ice, retreat of glacier and thinning of ice at the poles. Then melting has positive feedback in terms of increased melting, decreases ice, which decreases albedo, leading to further warming. So it is like something which is leading to kind of decrease in albedo and more of further warming. So some of the related things, and then some visuals. That one area, how it was in 1957, how it is in 1998. Some visuals that we can just quickly remind ourselves. But now looking at some of the effects of global climate change, maybe changing precipitation patterns. Some areas will get more water, some areas will have greater droughts. So maybe cyclones and hurricanes also will likely get stronger. So some of the concerns here as what could happen when we actually worry about this, and then worry about the studies using remote sensing. In coral reefs, as I talked, so even the reefs can be bleached, you can see, due to increase in water temperature, and then this can affect them, making more susceptible to diseases to which they would otherwise be immune. So their health is compromised, and then they're lasting there as a healthy kind of this object here in the aquatic environment. Then effects on agriculture, it is difficult to anticipate. Your productivity may increase in some areas and decrease in others. So because of this changing kind of weather conditions and because of the changing climate, so that can lead to, it is not everywhere. I'm not saying anything that is in favor of this, but it may so happen that productivity can increase in some areas and decrease in others. So that is just to look at anomalies or anomalous behavior. So that is more important. Then the rise in sea level, which can inundate the floodplains and river valleys. So that is even less farmland. So even that can be compromised. So in fact, rise in sea level in terms of agriculture, where even the kind of land farmlands which are there, and effects on pests. So where it will be like producing some effects on pests, whether it will be more resistant to some kind of conditions and then is difficult to kind of get rid. Then warmer temperatures may decrease soil moisture, requiring more irrigation. So what I'm looking at, talking about all of this, maybe looking at potential of researches in such areas. So here also, in fact, we had already discussions earlier, agriculture, location, elevation and altitude, where certain crops can be grown, which may change. So in fact, that also may be shifting. So what actually in the vertical profile of a mountainous region or hilly region or even otherwise, anywhere, you can see the different these climatic regions that we talked about temperate and tropical and polar and other climate regions. So when you actually look at the vertical kind of stratification, so that can change, the elevation can change. So that is effects. Then we actually next need to worry about this. Actually, El Nino and La Nina we have here as one of the important kind of parameters which can be in fact driven by the climate change conditions in terms of maybe their harmful effects. As such, they are supposed to be having a kind of revisit cycle of 3 to 7 years. But they are globally important. So wherever they happen, but they have some kind of global impact that they produce. So El Nino phenomena actually is referred to as El Nino Southern Oscillation or ENSO. So this actually is, as I said, has a important kind of atmospheric variable, and this has an average return period of 3 to 7 years. And it actually goes between the cycle of El Nino, the neutral, normal years, and then La Nina, ENSO cycle. So this is basically that way it is understood, and it has large influence both in the tropics and mid latitude. So that those particular kind of areas geographically, and more sources of forecast skill beyond a few weeks. So that is in fact that actually is something where more and more research is required. But basically, it is something like forecast in time. So how El Nino is coming and whatever is happening in an area where it is amenable to cause kind of its origin. So a normal year, when we say you have the high pressure in the Eastern Pacific and low pressure in the Western Pacific. In fact, that is the area where it actually happens. So you have the kind of the surface trade winds which blow east to west, so that easterlies across the Pacific Ocean, and they actually compensate the upper atmospheric westerly winds. So in fact, instead of westerly, so that actually starts trading. These trade winds start this changing this, and this in fact when you can see the trade winds, and then that turning as maybe in terms of why it is happening is because of warm moist air which is rising, then cooling and condensing, and then they form rain clouds here. Then normal rain circulation, and air pushes the warm water westward. So in fact that is somewhere that this is happening, and then in a non-El Nino year, the trade winds blow from east to west along the equator. So east to west is the normal thing along the equator. So trade winds are there. So normal condition here that you can see, and then such that pushing of warm water across the sea surface from east to west starts taking place. And then upwelling of cold water takes place off the west coast of Peru, together with more cold water supplied by the cold Peruvian current. So it is as a phenomena because this is confined to that geographical region. So now let us look at the El Nino. This is a normal year that is shown here. Now El Nino year, when we talk, the trade winds again they become weaker and may even reverse. So in fact, instead of maintaining their easterly kind of flow, so they actually can reverse. And then low pressure develops over the Eastern Pacific with high pressure to the west. So in fact, that is what is depicted here. And then you can see that waters off the coast of northern Australia become cooler. So in fact, some things which started happening, and then rainfall totals in northern Australia and Indonesia reduce, And the dry conditions often spread to India and Southeast Asia. So we are also not unconnected with that. So those dry conditions can happen. So this is there, and then rain falls in northwestern South America. So basically, so that kind of imbalance which is created because of this phenomena. So again, El Nino, so this is the visual of El Nino conditions, and here. So that is actually something which is having far ramifications, global ramifications. So that is why we look at this. Then El Nino impacts. So in South America, what impacts are actually seen here? Increased possibility of flooding on the western coast of northern South America in drier conditions. So in fact, the temperatures that you see here, in fact, whatever is recorded, it can show. So that is the kind of, you can see the scale, and warmest and the most kind of condition where it is happening. So in fact, and then the conditions which exist in different conditions, the dry conditions exist in different parts. So in fact, one can just see, and then this kind of factored kind of details which are there about this. So that anomalous behavior is more important, and that is what is happening. And then of course, this is that part where the weather conditions in southern Brazil, South America, and northern Argentina. Whereas again, coming to Australia and Western Pacific Basin, weaker monsoons across much of Asia, reduction in number and intensity of tropical storms, and increase in wildfire with the dry conditions. So in fact, it is not only that rainfall that is reduced, but the drier conditions which are reduced. So that in fact now we talk about wildfires increasing anomalously, which is that there's anomaly, their occurrences, many things can be associated. One has to just see these kind of phenomena. So El Nino and then La Nina will be just almost opposite to El Nino, but basically it is something which is act independently, and they basically are not associated with El Nino events. So in fact, they happen independently, and they involve the buildup of cooler than usual subsurface water in the eastern Pacific Ocean, and very warm waters build up in the western Pacific. So in fact, that temperature differential is there, and they create severe drought conditions in the eastern Pacific coastlands in western and southern South America. And very wet weather can be experienced in northern Australia and Indonesia. So this is the kind of reach that it has, La Nina. So La Nina, we are slightly away, but it is reaching up to Indonesia. So very strong air circulation, very warm water, and water which is cold. So this kind of differential that we see, and then this La Nina kind of this event takes place. So La Nina also is a kind of, again, we can say global phenomena. And then in a La Nina year, what changes in rainfall and drought may take place. So you can see. So we can see the patches were drier than usual. So La Nina year, the kind of these are the patches you can see recorded as drier than usual and wetter than usual. You can see wetter than usual, which is more wet. So it is, I think, huge area, huge geographical area which is covered. So I think there is, again, I'm repeating that all those are becoming subjects of research at local or regional level, and then we are not unconnected or disconnected to that. So I think that's as a phenomena, climate change, we are talking weather kind of variations and those things. So of course, the important to go somewhere back in the back of our mind, that is to sit and we know wherever we are working or any geographical area we are tackling, what could be the kind of larger picture there in terms of climate change and those kind of phenomena. Now coming to the satellite remote sensing, SRS, and climate change. So first part, I just like to point out about some of the conclusions of very good studies where already they are talking about satellite remote sensing has provided major advances in understanding the climate system and its changes by quantifying processes and spatiotemporal states of the atmosphere, land, and oceans. So basically, we are talking about spatiotemporal states. So what observables I was talking in one of the slides. So spatiotemporal of atmosphere, land, and oceans all. Then spatial pattern of sea level rise and cooling effects of increased stratospheric aerosols. So aerosols also nowadays, I think, in terms of this kind of atmospheric concerns, and in fact that is reaching through sea level rise, and then even in fact aerosols which are there in the stratosphere, whether that increase is of concern and aerosol itself is concerned. So that is one has to be careful, but we need to understand. Then unparalleled global and fine scale spatial coverage of satellite observations with observations which are possible. So in fact that scale is multi-scale that we say, even finest scale which is possible. So that coverage, and then global. In fact earlier it was very kind of you can say fine resolution, and then it is large area covered, but resolution were not that coarse. So that is, those conditions are now not there. So we have all these kind of capabilities. Then even short duration of observation series and their uncertainties still pose challenges for capturing the robust long-term trends of many climate variables. So that is what actually, if we look at the satellite remote sensing and the kind of data which are available through this, so this we can see, we can go back a few decades, whereas for overall climate change. So naturally we need to, and in fact that example of IPCC was very important, that IPCC is taking kind of data and details for climate analysis. They are actually pulling in data from various sources. So not on, so there we can only say we can contribute towards the later part where actually the data are available through satellite remote sensing. But in fact, there are other data in climate, climatic variables that we can see. But one can see you have the short duration of observation, maybe one limitation, but still whatever kind of the capabilities are there. So in fact, one has to see and where there are limitations, so uncertainties for capturing the robust long-term trends of many climate variables. So in fact, we may be somewhat slightly handicapped here, but still now the way the other such effects research kind of data collation agencies which are doing all this, so therefore can have the continuity and maybe pulling in of the proper data for climate variables. But we can contribute in terms of whatever is available and whatever best thing can be taken out, and focus on future systems to make better use of remote sensing in climate change studies. So that is one part. Then looking at the climate system at multiple spatio-temporal scales. In fact, that is again the capability of SRS, satellite remote sensing. For example, most efficient approaches to monitor land cover and its changes in time over a variety of spatial scales. In fact, land cover changes many times surpasses our concern of using satellite remote sensing in climate changes. So many times the improvement of meteorological reanalysis data, so that may be another thing when we are getting satellite data. So in fact, any other kind of data through satellite, this meteorological and other kind of data which are available. So there, in fact, better kind of validation and better kind of supplements can be there. And then there's one report of Global Climate Observing System of 2010. At that time, they had already kind of pointed out that 26 out of 50 essential climate variables are significantly dependent upon satellite observation. So right now, in fact, many of the climate variables, so some reference they had taken about 50 essential climate variables, out of that 26 are already depending on the satellite observation. So that importance part, so where we are becoming important as maybe player. And then satellite remote sensing are used for developing prevention, mitigation, and adaptation measures. So prevention, mitigation, and adaptation measures to cope with the impacts of climate change. In fact, this is a very important thing these days. How far prevention it can be practiced, mitigation, and then of course adaptation also with the changed kind of climatic conditions. So then satellite remote sensing can play a good role here also. So these are some of the kind of, in a nutshell, which is said. And as I said, this about change detection for maybe any kind of feature, biophysical materials and human-made features. In fact, they are dynamic and changing. So that is what actually is land cover and those details that we see. So basically, land use and land cover change basically is one of the major component of global change. So one of the, I think we can say, satellite remote sensing, when we actually are deploying, one of the very prime components one can see in terms of the impacts physically, which can be there, and then what changes are taking place. So with global change with an impact perhaps greater than that of climate change. So climate change may be connected to this, and they may have a to and fro connectivity. But land use, land cover change itself is a big kind of phenomenon where actually satellite remote sensing through change detection and climate change part when we want to connect. And significant effort has gone into the development of change detection methods using remotely sensed data. So naturally, any practicing remote sensing person like us would be knowing this, and then we just look at maybe when we do. So region of interest, so dimension of the change detection, region of interest, that has to be, in fact, how we go about it is, that is important, must be carefully identified and held constant throughout a change detection project. So that is one, that exactly that we say shape file or those things that we develop and change detection region, that area of interest that we have. So in fact, that has to be very properly defined, and then any temporal kind of changes that we want to do with the same kind of ROI, and it must be completely covered by end dates of imagery. So any number of imagery and number of dates that we can use, so it has to be completely covered. So if we have partial cover for the entire ROI, then that will not serve the purpose. So then basically failure to do so may result in change direction maps with data void. So if we do it for a ROI where we have this gap, then naturally there will be data voids which may be problematic when computing change statistics. So as one of the very important components, and one has to see the kind of basic considerations here also. And then remote sensing system considerations. So here basically we have to look at successful remote sensing change direction that we actually want to do. We need to look at sensor system, remote sensor system considerations, and environmental characteristics. Basically here, remotely sensed data, which we actually use to go for change detection, that is acquired by a remote sensor system, which can hold the resolutions constant, the following resolutions like temporal. So it should be of constant temporal resolution, spatial and look angle, constant spatial, spectral, and radiometric. So this is actually one to make sure that there should not be any variation, so that one has to look at the sensor consideration, these kind of characteristics for that, and then look at all these things, but there should not be any compromise. And talking about temporal resolution, it is again typically constant during change direction if possible. So that is very essential. And using the sensor system which requires data at approximately the same time of the day. So in fact, that is what we know the revisit time. So in fact, when any area which is revisited by the same time in terms of that equatorial kind of visit by Earth resources, satellites, and then any area which is covered. So it is that is to be ensured. So in fact, that is one of the basics that we already have in mind with remote sensing person. And acquire remote sensor data on anniversary dates. So for any change detection studies, anniversary dates are actually advisable. So maybe, for example, November 1, 2012 and November 1, 2017. Say for 5 years we want to do. Similarly, we can design our data sets. Then anniversary date imagery actually minimizes the influence of seasonal sun angle. So that is important. So it's not the features and maybe overall phenology available for any forestry study or any kind of other agricultural study or any, but basically the consideration is that the sun angle, and of course you have the plant phenological differences, so that can negatively impact and change detection project. So in fact, anything as one of the major covers. So what it can happen if the sun angle is in fact that is not ensured to be of the same disposition in different applications. And looking at spatial resolution, ideally the remotely sensed data are acquired by a sensor system which collects data with the same instantaneous field of view on each date. So that is ideally done. And then we have, for example, Landsat TM data. They have 30 by 30 meter spatial resolution on 2 dates, and they are relatively easy to register to one another. So if the same kind of pixel size is there, then we can have that ease of registering them and perform change detection using data collected from 2 different sensor systems with different IFOVs. For example, Landsat TM data 30 by 30 meter for date 1 and Spot HRV multispectral data 20 by 20 meter for date 2. Then one has to perform some kind of operations where we can do, and then finally resample and decide, and representative minimum mapping, then we have to decide and resample. So this is basically if you have this kind of a difference, then that is required, and then both the data sets actually brought to this uniform pixel size. So which has to be scaled down. And then of course, whatever in fact we use for change detection should be geometrically rectified. Some of the basics that we need to look at. And the spatial resolution, when we look at misregistration of the 2 images, may result in the identification of false change between the data sets. So that is one important reminder here. And then, for example, just misregistration of 1 pixel may cause a stable road on the 2 dates to show up as a new road in the change image. So any feature for that matter. So any pixel which is shifting that can. So this just to emphasize on that kind of importance that we actually look at. Then look angle also, remote sensing systems like Spot and QuickBird, they can collect data at off-nozzle look angles as much as plus minus 20 degrees. So one has to see where actually the kind of possible range which is falling within the similar type of acceptable event. And then 2 images with significantly different look angles can cause problems when used for change detection. So that is what another important thing. And this actually, one example can be seen from a spot image of a forest, which can be acquired at 0 degree off nozzle. So this will look directly down on the top of the canopy. Whereas if we have a spot image which is acquired at 20 degree of nozzle value, that will report reflectance from the side of the canopy. So then there will be straight away a difference here. then actually this is what is recommended, that acquired data with approximately the same look angle. So these are some of the things in one of the very important domains that we look at. Then spectral resolution when we are talking, ideally the same sensor system is used to acquire imagery on multiple dates. Then for multiple sensor, bands are selected which approximate one another. So one has to just look at the equivalence, so band equivalence. For example, we have Landsat MSS band. So earlier we had 4, 5, 7 green, red, and NIR, whereas its equivalent in spot is band 1, 2, 3. So that is green R NIR. Same thing, but different band designation. And similarly in Landsat ETM Plus also, if there is a different band designation, the same wavelength ranges, green, red, and NIR, but wavelength bands 2, 3, 4. So I think all these some basics that we actually we have to work on. One, if we want to work on maybe global coverage and maybe the kind of regional coverage of land use land cover kind of changes. Radiometric also, you have this ideally the sensor systems collect the data at the same radiometric precision on both dates. So that is the most ideal thing one can expect. But when we are pulling in the data from different sensors, so what you can have this disparity where your bit value will differ, that radiometric value. And then, for example, in the radiometric resolution of data acquired by system like Landsat MSS1, so they had 6-bit data, 64 or so levels. This is compared with data acquired by a higher radiometric resolution instrument, for example, EM with 8-bit data, so maybe almost 256 real levels. So the lower resolution data, for example, 6 bits should be decompressed to 8 bits for change detection purposes. So I think these are all the types of kind of some cautions in terms of using. So that is we actually as I think majority of us as practicing remote sensing persons might be knowing, but just look at these kind of basics that one has to not compromise. Then brightness values associated with both dates of imagery are converted to apparent surface reflectance, which eliminates the problem for this. So this is actually some of the kind of practice that we actually follow in this change detection thing, one of the very important domains in this land use land cover chain to large extent. Now looking at this Earth observation era that I talked, here looking at some of the capabilities, say for example, Terra and Aqua thing. So in fact, some of the sensors which are there, say for example, MODIS we talked, and then MODIS also will see. So that we will see that some of the products which are already being tried and made available through NASA Earth observation. And you can see atmospheric climatic parameters when we talk. Say for one of the examples we can take of aerosols. So atmospheric aerosols play a major role in Earth's radiative budget. So that is what if they are present in whatever kind of density there in the atmosphere, so that one can see, and then that can have a major impact maybe in terms of overall radiative budget. So radiations incoming and outgoing. Then MODIS about NASA's Terra and Aqua. So that we all know this. The detail full name of MODIS is Moderate Resolution Imaging Spectroradiometer about NASA's and Terra. So this is used to monitor aerosol optical thickness. That is basically proportional to the aerosol total loading. In fact, that loading is the correct term to use, and then that optical thickness converts back, and then in fact that gives an idea. And size distribution also. So that is integrated on the vertical column of the ambient undisturbed aerosol over most of the globe, oceans and the moist parts of the continent. So that is on this part on a daily basis. So this is basically acquired on a daily basis by MODIS. So in fact, that is again I am trying to tell you some of the important parameters, atmospheric parameters being acquired by the remote sensing sensors and the data which are available, and that can lead to what kind of contribution in the climate change studies if we are concerned about atmosphere also. Aerosol climatology. So to monitor the sources and sinks of the specific aerosol type, such as sulfates and other industrial or urban aerosol and biomass burning aerosol. So in fact, these kind of segregation of the aerosols, so then that can be understood, and to serve as inputs for climate modeling. So that is again here actually that is the connect that we have to detect some of the fingerprints of anthropogenic climate change, like smoke and air pollution. So in fact, these are the things. So where anthropogenic climate change, that contribution is coming, and these kind of fingerprints where aerosol can be picked from either smoke or air pollution, and to perform atmospheric corrections of remotely sensed surface reflectance over the land. So maybe these are the kind of data which is available, and then which are available, and then these things are performed and which can be useful. And MODIS aerosol product monitors the ambient aerosol optical thickness over the oceans globally. So ambient aerosol optical thickness over the oceans globally and over the continents also. So this is basically the way it is acquiring, and it aerosol size distribution is derived over the oceans. In fact, this is what is the difference, and the aerosol type is derived over the continents. So types are derived over continents, and size distribution is derived over the oceans. I think that is how it is done, and there are actually segregation of fine aerosols, anthropogenic and pollution, and coarse aerosols, natural particles and dust are also derived. So in fact, here actually you see these two products. One is actually showing the first type, where you have the kind of product, you have the specific aerosol types, and then you have the kind of aerosol kind of this coarseness and fineness. So that basically is you have the types which are varying in terms of their size. In size, you can say size, rather you can say in terms of their origin, either natural kind of aerosol or this their kind of anthropogenic emission which is there. So in fact, these are all important when one goes into this domain for examining the atmospheric kind of changes. Now, carbon monoxide and then thereby methane. We can say no methane measurement directly, but there are other sensors that would be there. But here, talking about this carbon monoxide and methane, there is one sensor that is measurement of pollution in the troposphere, MOPIT. So that is in fact is one sensor about the STERA satellite. And then full range of effects of the increased concentration of carbon monoxide basically is not fully understood at present. But it is believed that carbon monoxide is photochemically active. So carbon monoxide is photochemically active, so and plays a major part in the concentration of hydroxyl radicals in the troposphere wedge. So in fact, that is one of the implications that one can see, and that can lead to conversion. So increased carbon monoxide may deplete, first of all, depletion of tropospheric hydroxyl radicals, thereby reducing the yearly removal of many natural and anthropogenic trace species, and this effect may add to the increase of methane. So then, because of that extinction and those trace species which are going off, then that can lead to addition of more methane. So that way, in fact, is in fact some kind of indirect indication, which in turn would further reduce wedge concentration. So that is in that way it has to be factored and understood. So basically, looking at the carbon monoxide. Then increased carbon monoxide may also indirectly intensify global warming and perturb the stratospheric ozone layer by increasing the lifetime of trace gases such as methane and chlorofluorocarbons, so CFCs. So in fact, the CFCs culprit of these ozone holes and those things, and then methane also. And in fact, that is not directly measured, but these in fact can indicate. And this again, as I said, this global measurements, this is done by this MOPIT or Terra satellite, and then that can lead to indicate the concentration of hydroxyl, which is one of the important and difficult species to measure from space. So that otherwise it cannot be, but it can be related to that carbon monoxide. It can be derived through this, and the global carbon monoxide and CH4 measurements from MOPIT can be used in parallel modeling efforts to advance our understanding of global tropospheric chemistry and its relationship to sources, sinks, and atmospheric transports, which can be determined from other data. In fact, these are all details which one can always find with the data sets which are available already on the NASA observation site. So it is, and then one can see what other researches which are available through that. So in fact, this is again referring to those sources also where one can find more when we have an interest in this. And understanding biogeochemical cycles and their intimate interrelation with each other and with climate will lead to better predictions of possible effects of anthropogenic activities. So in fact, that is again retrieved carbon monoxide total column for using MOPIT data for a particular reference rate. It is just shown here. So that concentration more or less, maybe it is where red is alarming, where it is not red, and green, and those kind of variations are shown. But one can find out, and these can be downloaded, which are available in NASA observation. So coming to another important factor, atmospheric climate parameters, say cloud fraction. So the cloud fraction is also one of the products which is available. So this basically is the portion of Earth's surface covered by cloud relative to the portion of Earth not covered by cloud. So that is what is that unit area of an Earth, how much area is covered by cloud and not covered by cloud. So that fraction. And this is derived from 1 kilometer pixel resolution cloud mask product made from radiance and reflectance measurements of Earth, which is collected by MODIS about NASA's Terra and Ica satellites. So this is one product. So the visual that is here, you can see here, the cloud factor. Then cloud optical thickness or cloud particle radius. Here, basically, clouds strongly modulate the energy balance of Earth through their interaction with solar and terrestrial radiation, as demonstrated from both satellite observations and from modeling studies. So, in fact, something like modeling studies plus satellite observations. So, that is in fact in that combination. And knowledge about cloud properties and their variations in space and time is crucial to study of global climate change. That is greenhouse gases, as general circulation GCM simulations, and because that is indicating the climate-induced changes in cloud amount and vertical structure, with a corresponding cloud feedback working to enhance global warming. Of course, I'm again saying that when we are concerned with this domain, then we need to look at all those kind of fine details which are available, and it is possible to look at that. So those researches still using the remote sensing products, and then this is again MODIS instrument, which is retrieve the cloud optical thickness and effective particle radius, and then actually that is derived from the daytime multi-wavelength reflected solar and emitted thermal radiation. So some kind of algorithm they might be having for this, and then that is generated. So this is the kind of representative data. So how it looks, maybe out of the global data, I have just taken this one in a very small scale, it is to reduce to lower size to show here. Then cloud water content. So this is a global map of cloud water content, this is a data product derived from measurements of cloud optical thickness and cloud particle radius. Again, similar way, but collected by this MODIS. And this is an image which is generated and showing how many grams of water is contained in a given 1 meter square column of cloud. So 1 meter square column of cloud, how many grams of water is contained. So that is something. And then these are, of course, not to just one time for one time measurement. If these products are available, then what we are talking about global climate change, those things. So that can be facilitated by studying these parameters temporally and spatially, different regions and over the globe, or maybe globally also. In fact, the entire data set is available for at global coverage. And looking at this average LST day and average LST night land surface temperature. This, when we talk about LST, this is a good indicator of the energy. So in fact, the visual above is day and LST night, the lower one, taken from the same NASA Earth observation. So land surface temperature is a good indicator of the energy balance at Earth's surface, because it is one of the key parameters in the physics of land surface processes on both regional and global scale. So in fact, how seasonal variations could be there in LST, and whatever the LST in a kind of a particular time of the year is characteristic of an area of a particular type of land use, a particular type of region, you can say. That is one very important. And then that basically overall, when we look at that energy balance of Earth's surface, so in fact whatever is falling on the Earth's surface and whatever is getting reflected, whatever is absorbed and transmitted, so those kind of components, if we imagine falling radiation, so then LST is one of the very important kind of considerations there. And then LST integrates the results of surface atmosphere interactions and energy fluxes between the atmosphere and the ground. So this is what is important. So out of this, what energy fluxes are falling, and when it comes and when it goes back from the ground. Therefore, LST measurements are required for a wide variety of climatic, hydrologic, ecological, and biogeochemical studies. So this is straight away connecting to this again, this climate, hydrology, ecology, and biogeochemical kind of studies, where you can have this factor as one of the important kind of parameters in that. And MODIS satellite uses the most current, accurate radiative transfer models and lookup tables, how they are converting. So now this actually is slightly shown here, and land cover emission coefficients to produce an LST data product, which is accurate to within 1,000 at 1 kilometer spatial resolution in clear sky conditions here, and LST day, CMG for daytime and LST time. So that imagery types that is described. So once you go to that site and try to find out whether these kind of kind of notations you will find, and look at another ones. Maybe sea surface temperature. This is an accurate sea surface temperature climatology is fundamental to the effort to model and predict natural and anthropogenic climate change. I think SST is one of the very important things, even for our normal cyclones and hurricanes and these kind of typhoons which take place, apart from even looking at the El Nino angle and those kind of things. So high temporal and spatial resolution of satellite-based climatology is an inherent advantage over lower resolution traditional climatology that depends on in situ or blended in situ and satellite data. So that is in fact something which is in fact picking up now. So better temporal and spatial resolution of satellite data availability is actually facilitating this. So SST climatology, basically when we talk, that comes from data acquired by NOAA, National Oceanic and this kind of that advanced AVHR, or rather that sensor, advanced very high resolution radiometer sensors on NOAA 9, 11 and 14 satellites. So NOAA satellites, and there this sensor, AVHR sensor. So basically these are some things, and then one visual that I'm just put on the display, that you can see the range -2 to 35 degrees C. So that kind of a SST that is recorded. So overall the global dispersion. So looking at sea surface only, so the temperature variation wherever sea is there, and then one can see and one can monitor. So this is basically something greatly to be aided in terms of climate change studies. As again, I'm just trying to, I'm not repeating rather, but it is like to kind of give an emphasis on the connect that it has. So now I think there are more parameters also available. So one can see and find out when you actually have the segregation as maybe atmosphere, energy, land, ocean, and similarly you can see on that site, and then different types of products which are available. As I said, MODIS 40%, then there are other satellites which are there. And then I think coming to something which is like almost narrowing it down to that indicator that we actually mostly are concerned when we look at any news item or hear about any news item that yes, glaciers are sinking, snow cover is sinking. And then I think that is one, I'll not say as a layman, but one of the concerned persons for global climate change. We very much kind of try to understand that what is happening, and that may actually confirm whatever is being claimed by the climate change scientists that we hear, that energy and mass fluxes which govern the surface mass balance, they are directly linked to atmospheric conditions and are modified by topography. So when you look at the maybe this is surface mass balance of glacier and those kind of things. So glaciers, when we see here, then there's something known as mass balance, right? So that is a kind of surface mass balance where you have some kind of a almost like constant line which has to be there throughout the year, where to be frozen part, like it is not freshly fallen snow, but it is that part of the glacier where it is. And if that there is a shift in that, then the problems are there. So glaciers are sensitive climate indicators because they adjust their size in response to changes in climate. So that is temperature and precipitation. So basically, these are the two important factors: temperature and precipitation. So how glaciers will behave. So they are sensitive to these indicators. And glaciers are also important seasonal to long-term hydrologic reservoirs on a regional scale and a major contributor to sea level rise on a global scale. The positive part is that standing tower of water, that is fresh water that we have in glaciers, which are intact. Whereas if they are melting unduly because of the climate change, then there is another negative side to it, is major contributor to sea level rise on a global scale. So that is what we have to worry about, that is that climate change is taking place. So now here for us, it is, since we are studying, we are actually trying to get connected to it more academically in terms of climate change. So we actually are trying to look at that how this is happening. So we may have to worry for that, about that phenomena itself, whether it is going an indication of where the glaciers and snow itself are at peril, at risk of getting kind of washed, totally kind of vanish. So those kind of things. Now, with this kind of concerns, one initiative was taken in terms of creating the Randolph Glacier Inventory. In fact, this glacier inventory was in fact taken into consideration when that space-based observation could aid into the mapping of such glaciers and create an inventory globally. So that was one initiative taken by Global Land Ice Measurements from Space. So GLIMS is a program under which it was done. And this is very important to see that what Randolph Glacier Inventory had come out was all totally based on the space-based observations, and just like a, you can say, baseline information to be created, and then other researchers to get a kind of advantage of referring this to referring this for any kind of changes in the kind of mapped glaciers which are there, a map of glaciers for one time, and a collection of useful attributes. So there, and then other associated fluids are also collected. So one time map, and then this basically complete data set of glacier outlines was compiled from a wide range of data sources from 1950s to 2010. So data sources from other sources, but basically to facilitate one part is whatever is available through space-based observations, or maybe in future when these are all kind of done using all the sources, then this RGI is going to help the people who are going to use the space-based remote sensing techniques to either monitor or do any kind of research where they have a concern of finding out the status of our inventory of the glaciers which existed here. And then regionally variable accuracy of the glacier outlines leads to poorly quantified uncertainties. So they basically that if you do maybe some kind of one kind of maybe compartment by compartment, then in fact somebody is doing one part in his or her own kind of understanding, and then other agency or person is doing different way. So there could be that maybe some kind of mismatch of outlines. So that can be something like leading to uncertainties, so quantified uncertainties. So that is one of the things why it was made uniform. And so therefore these uncertainties which were actually earlier prevailing, so along with the regional variation in the minimum size of glaciers included in the inventory. So and such those things were removed in this inventory. So that is what, so in fact available kind of things which were there, they were pulled in, and then in fact how they have been factored after removing such uncertainties. So that is what if this was not available at a global level, we would have been working with our that area by area, but there could be mismatch from what I am seeing and what other is seeing and what they have a correct criteria. So everything that sensitivity is there, and then in fact that part accuracy also. So that part was factored properly, and the subdivision of these contiguous ice masses, total number of glaciers, everything. So in fact everything to be factored properly. So that is why this RGI was created. And then with the interest of this global climate change studies only, and then current best estimate, whatever actually has been found out using these inventories, is about 1,70,000 glaciers covering a total area of about 7,30,000 kilometers squares. So they have certain kind of size limitation. So actually they covered 19 regions of the globe, different geographical regions, and actually they covered under that. So after summing up, they actually found that nearly 80% of the glacier area found in regions like Antarctica and Subantarctica, Canadian Arctic, high mountain Asia, even our Himalayan areas, Alaska and Greenland. So one table we can just quickly see. So under this, whatever regions they have covered, these are the regions, and then under which various number of glaciers that they have. So how they have counted this number of glacier area, percentage of total area, and then tidewater fraction. So that is something they have derived out of maybe some kind of available information. Then mass equivalent to gigaton, this minimum mass maximum gigaton, some estimates. Then mean sea level equivalent also. If that is that much of glacier will be how much millimeter equivalent to sea level when you consider globally. I think all those interesting to see that global climate change. If you want to do study, then these data are available there, and then one can take that as a baseline data or baseline information. And in fact, when we actually look at this kind of scenario where we worry about snow and glacier, so slightly I'm trying to bring you back to that part where actually as glacier and snow cover as a indicator of climate change, and where actually some of the interest I have, and maybe as a person involved in some of the researches here in these areas. So maybe some of the things that we actually normally look at, prediction of future changes of snow coverage and snow melt runoff. So some things that one will become concerned if suppose you are working in a catchment area or a basin where you have the subalpine or alpine conditions also exist in that basin, and you are in fact entire runoff of that watershed or that basin certainly will not be only factored by rainfall, but it is overall precipitation of the basin, whereas you have the precipitation in the form of snow as well as rainfall. So how that can be factored. So many and similar other things. So let us see, when we look at these kind of predictions, we look at the models that can predict meltwater runoff at a daily time scale. And then that is actually important from the point of view of water resource management, then flood hazard assessment, and climate change impact studies. These three broad things are told here. Here basically Water resources management would be for the downstream available of water resources for various purposes. You have the hydroelectric power projects, and then you have the agriculture, and then very good kind of water resource, water supply to the downstream areas and in the plain areas and along the streams also. So for the freshwater supply, then flood hazard. I think there is sometimes there is a kind of overflow and overtopping of this because of lot of discharge in the basin. So then flood hazards around those the areas in the downstream or maybe the plain areas where the river reaches. So I think mostly the snow and glacier fed rivers that we have like Ganga and those rivers that we already keep on hearing about these, which is still active now. So not only that, compounded by the rainfall also in that. But overall, in fact, it's a seasonal kind of study, and one can see how whether it is due to climate change when there is anomalous behavior or not. So then actually these predictions, when you see for future changes, then one has to see in the sense of large volume of data to be factored into those models, and then look for such kind of prediction models to apply or maybe generate. The seasonal and shorter term variations in stream flow reflect variations in rainfall. So maybe seasonal and shorter term variations when we look at. So their stream flow may reflect the variations in rainfall. So that can be something that one can understand. Where higher latitude precipitation is snow and not rain. So that is what I was trying to say. If snow has already fallen, there is snowfall in the higher reaches, that is sitting here, there, and when it will melt, then only it will reflect in the runoff. And then runoff depends on heat supply for snow melt rather than the timing of precipitation. So then I think that energy kind of implications of that, and then what kind of this heat supply will be available for snow melt and when it will be available, and then I think seasonal considerations come there. So exactly not the timing of precipitation that matters. So in fact, that is what is important in these models. The hydrological importance of snow is not restricted to areas where it lies for months. So that is what it can. It is lying there, and if it is cold, and when it is starting melting in some other season, then it can lead to some kind of maybe availability of resources, unusual kind of. I'll not say resources, but unusual kind of flow and discharge, and maybe after many months when it was lying there and it was frozen. And then meltwater resource lies in its reliable occurrence at a particular time of year. So one can see this cycle and understand, and basically that is actually calls for a necessity of accurate prediction. And in general, snow melt models can be divided into two types of models. We have one is energy balance models, another is index models. So let us see what are the inputs. So in fact, here a lot of remote sensing and other inputs are nowadays being factored here. So temperature index model, when we look at, we have the input parameters like air temperature, precipitation, snow covered area, then rainfall runoff coefficient, critical temperature, temperature lapse rate, and time lag. So these are some of the input parameters which actually can give to output, give rise to output like daily stream flow, seasonal runoff volume, and basically one can see this does not consider the spatial variability of physical processes for the model input and calibration. So it is only those points where it is all calculated and how much it can produce. So it could be applied with limited amount of available observed data set. So you can have limited amount of observed data set, and based on that, this model can work. And the another model that we see is energy balance method, where you have the air temperature, then radiation, short wave and long wave, these components, then precipitation, wind speed, relative humidity, snow surface temperature, albedo, snow cover area, cloud cover, pressure, elevation. So snow melt depth and evaporation will be the output. So snow melt depth and evaporation comes out as output of that. And this basically requires large amount of input data for model simulation. So this basically are two kind of considerations and two types of methods. But you see what kind of output will be available and what could be the limitations there. So depending on that, but these are some of the widely practiced models. There are many more. So just to give you a quick idea, and fundamentals of snow melt modeling, when we look at, we have the first of all, you have the meteorological data, then you have to extrapolate and probably work out the meteorological details at the snowpack. So it is overall meteorological data, then extrapolate and make it maybe just kind of representative of the meteorological details of the snowpack. Then from there, you have the temperature down leading to snow melt, then rain, the runoff volume directly going into the model, Then you have the new snow, freshly fallen snow, then snowpack accounting. Here you have the depletion as input, then snow covered area. In fact, that is one of the factors. And here actually you have the melt rate. So these two, and then here the runoff. So they actually come out here, routing and formally you have the kind of association of all these finally can be seen as quantity of the runoff. So basically here you can see the transformation of incoming precipitation to outgoing stream flow. That is basically the activity here. And losses to the atmosphere, temporary storage and lag and attenuation. So that actually has to be factored. And simple regression equations and other black box approaches through conceptually based models to physics based models. So in fact, somewhere you have to factor those algorithms where one can work out. And then most snow melt models are rainfall runoff models. Then they extrapolate available meteorological data to the snowpack in order to calculate rates of snow melt at different points. Then integrate the snow melt over the current area of the snowpack in order to estimate the total volume of snow melt water that is there. So basically, these all majority are rainfall runoff models. So basically, what you get as precipitation, and then finally what goes out to the basin outlet. So in between whatever happens, so that has to be factored. And then even you have the physics-based models where you have to conceptually based models or physics-based models maybe. Then another traditionally we say black box approach is where you just have the factors just before you, and what best method you find you can apply and finally do that kind of mix. So in fact now just another kind of depiction of this basin level snow melt runoff modeling using remote sensing input. So now here my idea is just to show you that something like snow covered area percentage and time, cumulative temperature and cumulative snow melt. So in fact, so that is something which is some consideration which is taken here into consideration. But you can see the important kind of inputs that we have, whatever kind of observed forecast or normalized meteorological data you have, the temperature daily average max min, then lapse rate is calculated towards temperature contribution into this. Then climate change algorithms are there, and you have the remote sensing data where you can in fact interface the snow cover, daily snow cover, ice extent of each zone of unit wherever you are studying. So different height zones can be factored. Then precipitation data, so the critical temperature in between, and then precipitation. So what daily precipitation type total of each out of each zone, and then actually thereafter the other kind of inputs which are coming, degree day total, and then you have the digital elevation model data, elevation zones that you factor here. Degree day coefficient is calculated. So zone or unit of snow melt. Then coming to your runoff coefficients we are getting added here, and then rainfall. So this basically snow cover thing is finally contributing to precipitation, and then going to rainfall, transitory snow melt, snowfall, and then ultimately all arriving here into one is directly to zone or unit runoff or runoff coefficients, and then down here in lag time and then basic runoff. So in fact all those things in a hydrological model where you can see important part where we are talking about this climate change, where we are talking about this snow melt runoff as a basic indicator of that. So if that is usual runoff and usual predictions are working in terms of the time period which is to be covered, or maybe for future, or maybe these variations are recent variations which can be factored into the models in different seasons. So one can see that versatility and accordingly apply the model. And then of course looking at these impacts of snow melt, we look at the hydrological importance of snow, not restricted to areas where it lies. So in fact, as I said, that snow is sitting there somewhere, and then when it is coming as a discharge into the stream, it is beyond the rainfall, but it is something which is sitting still, it is contributing to the stream, sometimes positively, sometimes negatively. If it is coming in excess of its the channel capacity, sometimes many times we have heard about the Glough glacial lake outburst for flood and those kind of things. So if that happens, then large volume of water is drained, and then that is a different way to understand then this global warming. In fact, that is a point one can keep in mind. Otherwise, if normal kind of melting, it is certainly a resource sitting there, and meltwater is an immensely important water resource. So that is what is to keep in mind. In geographic areas dominated by snow melt hydrology, they are more susceptible to climate change as it affects the seasonality of the runoff. So that is seasonality of runoff. So even you can see beyond rainy season, and then you can see that what melting season, snow melt runoff, how that can behave. So that also can be an important factor in that. to understand the basic behavior. And accurate estimation of the volume of water stored in the snowpack and its rate of release is essential to predict the flow during the snowmelt period. So basically, this is very important. So, what accurate estimation is possible that is available in the snowpack. So that is what, and then rate of release. So these are important inputs into that. And flooding in the downstream areas can be detected with proper hydrological model prediction. So that is also another important thing. So that why these hydrological models are important. And then optimum management of the snowmelt water. So this is again snowmelt water, how they can be better management of that. So that is out of this impact. And then I think since we have talked a lot of this, and finally looking at this variation in the snowfall and then depletion of snow cover and glaciers. So one kind of clip I can just show. You can see different years how it is depleting the snow cover Himalayan area through pulled through Google Earth. Sorry, just slide show mode and leave it to you. Okay. Okay, so it is changing, and you can see overall decrease that is being recorded of late. Okay. So decrease. So, yeah. So in one go you can see here. So this is available in the Google Earth. You can always see and this. So basically now here the concern comes that whatever we do, whatever research we do, finally look at those areas and where it can be as indicator, it can be found, and then where whatever kind of different techniques that we have at our disposal in remote sensing. Whoever is specializing in whatever research, but climate change is a very huge domain. I don't know. I don't think I have covered everything, but I have tried to touch upon many things which could be of interest in terms of the research where the data are available and more can be explored and found out. And then somebody who is specializing in one domain certainly would like to find out more in that area. So with that kind of presumption, we have to find out our kind of areas where we actually like to go forward with this climate change kind of research. So thank you. So thank you for your attention. So I am done. I invite any kind of discussion points that you might be having. So Dr. Rathod, over to you, and then if there are any discussion points, I am there. Dr. Rathod? Okay, maybe. So I think other participants also, yeah. So I can interact with you if you have something else.
Hello, sir. Am I audible?
Yes, you are audible.
Sir, I have one question regarding the climate change. Like
Yes.
various working is going on the climatic models, and different data sets has been published by the different agencies for global using global climate models for future projections. So
Yes.
there are different scenarios of RCPs like RCP 2.5, 8.5, 4.6. Which scenario is we should going for? Which scenario for our work? I mean, what does it actually depicts?
Actually, those scenarios are depicted in terms of maybe when you actually look at the global climate model and regional climate model and you scale it down. So then one has to connect to that. And in that sense, where you connect those kind of scenarios. So right now, since what I have talked here is straight away those factors which where we can have the remote sensing inputs. In fact, GCM and RC
Disturbing. I can't hear you properly. Anything?
I think there is some problem. Yeah.
Okay.
So, so that is why I would just say that since the scope of presentation is keeping out that thing. So right now I won't like to go into the detail of that, but the only thing when you kind of scale down from GCM and RCM and those things, so at that time you have to look at those kind of scenarios.
Okay, one more thing, I guess these data sets have been interpolated based on the historical data sets. Am I right, sir?
Yes.
So, will it be, I mean, optimum to use these? I mean, how reliable is this data set which are future projected climate models?
you talk about this IPCC thing that I presented,
Yes,
Intergovernmental Panel. Yeah, in fact, they have tried to, in fact, cover from 18th century till now from various sources. So there is a huge exercise that they have done. And in fact, as a common man, also we hear about their predictions and their kind of findings, and then that is one of the globally accepted kind of report by all the countries of the world. So
okay.
there actually we have to rely on their data. So they have their own way of validation and the kind of historical data that they
Yes,
actually
because we
collate
don't
it.
have any future data otherwise.
No, actually, no prediction. There could be predictions. So predictions is a scope of again research by us also, a researcher like
Yes,
us.
yes. Mhm.
Okay, so that will be very interesting to look at that. In what way they have come up to that point, and beyond that, what could be predicted using their kind of information which is available.
Okay, sir.
Lot
Okay,
of
thank
research.
you.
Yes.
Thank you, sir.
Any other question?
Yeah. Any other?
Participants?
Please.
But they also care about whether they have food, whether they have an income that can make
Yes.
money.
Somebody.
Yep. We have time, participant,
This is
for interaction.
say that there's look it out.
Yes, Mr. Pankaj.
अफगानिस्तान से अपनी सेना की वापसी के फैसले पर दुनिया भर में अमेरिका की आलोचना हो रही है।
Mr. Pankaj, you have any question?
No, you are not audible. Only he was speaking, but not audible.
Yeah.
Any other participant?
Any other?
Just Dr. Saugata.
No, sir, no questions.
Yes. Okay. Okay. Since you came in video, so I thought. Okay. So, any more questions of any point of interaction? So, by and large, it was my effort to put together some of the, maybe I'll not say exactly I decide about frontier areas, but some of the frontier areas which are there in our domain. Yes, that is how I try to factor my entire spread out. I have not concentrated on case studies, so that is one thing. So if you would have liked to see the case studies, so I have kept out that thing out of the scope of this lecture. But overall spectrum which is available.
I think, sir, no question.
Yeah.
Participants,
Not that heavy.
don't have question, then can we sum up this session?
So my idea was to promote remote sensing.
Yeah.
For all these researchers. So
Yeah,
for this climate change research, promote remote sensing. So,
yeah, you covered, sir, almost all the areas of frontline.
Sir, it's a outstanding talk because I got a lot of
yeah.
overall knowledge. Especially, I didn't go to the new IPCC report that much. So those 3-4 slides helps a lot.
Okay. Okay. And probably your area.
Yep.
Yeah.
Yeah, that I like because that's make me refreshed.
Not as
to listen.
Any kind of detailed analysis, but I think these are something which can use in such areas.
Yeah, so to listen one subject from others, it really helps a lot. That how I should express the subject and what are the gaps. Sometimes it comes in our mind, so it helps a lot.
You are yourself.
So just I'm adding one comment by I think the last speaker, who asked the questions. The future climate. See, there are a lot of different parameters, and now we are more concentrated on the anthropogeny. So mainly, future climate depends upon the emission inventory. How perfect we do the emission inventory, and all the developed country and even included we are quite good to make those emission inventory. But there are a lot of countries which are not well developed. So the emission inventory from those sides are not as a good input for the climate model. And when your input is not good, usually the output comes. So which is they show as a forecasted, that is the in general considering the extreme one, but usually we will not face that level if we can consider the Mother Earth in much before. So that much I can say. And nowadays the perfection, yeah.
Or even segregating that part, natural and so overall. Yeah. So their characteristics are also known. Accordingly, the study has to be.
Yes, sir.
So then, Dr. Rathod, there are no more. I think
Yes, sir, I think now so we can conclude this. So thank you, sir, for delivering a nice lecture covering all the aspects of climate change. I again again thank you very much, sir, for giving valuable time and supporting me in this Atal FDP, conducting this Atal FDP as a resource person and as a convener of this Atal FDP. So thank you, sir. Thank you once again.
Thank you. Thank you all. Thank you all.
Thank you, sir.
So participant, now you can have break, and we will join again at 2:30 the valedictory session of this Atal FDP. So in the valedictory session, we'll again meet and we'll discuss further course. Okay. So have a break. And we'll meet at 2:30. Thank you, Padre. Thank you, sir. Thank you.
Thank you. Thank you. Okay.